All right, welcome back. So our next talk this morning is Arun Ram from University of Melbourne to tell us about varieties and polynomials.
Here, thank you, Chris. So I do want to just say a word, just a short word to start. My wife's name is Jay, and when she and I were starting our road together, right at that time, we met a young couple, Ari and Dan, at the same time. And of course, immediately there was just an immediate bond there, and we became very close friends for a long time. And so Jay couldn't come to this meeting, but of course, the last couple of weeks, we've been preparing at home, and we think we've gone through all of the memories and something. And there's something that we just kept coming back to, and that is that we're just sort of keenly aware of how blessed we were to have this friendship for so long. And so, of course, I'm talking about things that there are young people in the audience, and it's 150 years ago. But I think the motto is really, Dan and Ari, they have been focused, chin to the grindstone, just wonderful people the whole time. And I think if you do that, there's a lot of uncertainty when you start your career, and we had that uncertainty. I remember together worrying about it. But if you just do what they did, then you too, before you know it, you'll be saying, yes, we have led a blessed life too, with beautiful mathematics and wonderful friends. So that's what I wanted to say about them. They're very special people for me and amazing people. So this story I want to tell is also an old story in the sense that when I was a graduate student at San Diego, Adriano Garcia was working with Procesi and with Mark Heyman and had come across these crazy objects, at least for me, crazy, modified Macdonald. I couldn't understand why you wanted to modify anything. It was, but there were these modified Macdonald polynomials, and Adriano wanted everybody who was in his circle to get into these things, and I couldn't figure out where to put them in my head. It just didn't fit. So I guess I'm slow, and now, however many years later, what did we say, 150 years, I finally have a place to put them in my head. So I'm good. That's the story I want to tell. And I'm going to tell it absolutely non-historically, because I want to start right at the very end of the way that I want to think about these objects. So I'm even going to change them. They're not even Macdonald polynomials anymore. They're just elements, Macdonald elements. So let me write the first one. I'll call it integral form. Hopefully I can write semi-readable on this like that. So the integral form is called J mu, and it's going to depend on two parameters, Q and T. And what it is it's a generating function. So it's a sum over nu, and it's a cardinality of y inverse I gamma nu I of u mu k kappa nu. So that's the object there. So I want you to think of me that I'm a pure combinatorialist. I don't care about anything except counting things. So, and here, this is what we want to count. This is a cardinality. So there's some object there, and I want to count the number of points in this. And if you've gone so far as to maybe study Stanley's book or something, you know that you should do it with a generating function. So I want you to think of this thing as a generating function. It's just a generating function for all these cardinalities, and they're labeled by these kappa nu. Okay? So that's the integral form. And then there's the modified elements. And the modified are called h mu tilde qt, again, two parameters. and that's a sum over pi this time. And this is a cardinality of yi pi inverse of u mu. And it's going to be, instead of kappa, I have a different parameter, which is called 1 pi. All right, so these are two different generating functions, and hopefully they look a little bit similar in the sense that whatever we're counting, the notation for these two things that we're counting is somehow a little bit similar. All right, so you've got this picture now. All right, good. So that's the first thing, and of course, since we're working on an iPad like this, you have to remember. You have to remember that, and I'm going to go now to try to set up this story. So I'm living in the world. Oh, I'm living in the world of loop groups. So in the same way that John was doing, I'm going to take an arbitrary reductive connected group, and I'm going to think of it as a group scheme so that I can evaluate it over many different rings. And the first one I want is the field of rational series. So this I'm going to call G tilde. That's my favorite loop group. And it contains, you all know that this, that I don't know, I'm a purely a combinatoric, so I don't know any topology. So it contains a maximal compact subgroup, which of course makes no sense in this setting, which is this same group, but over the ring of integers. All right. And then we have a nice map, which is setting epsilon to 0. So these are just formal power series, so you can set epsilon to 0, and that takes you to the finite group of Lie type, which I'm going to call G, which is GLN over FQ, except that GLN might be type E6 if you want. Just I want the picture to be like that. Okay, so this contains what I'm going to call P pi. And then we've made the first connection to my previous slide. You remember the previous slide, there was a pi. And this is the same pi. Now this is a standard parabolic. So it consists of upper triangular matrices like this. And the block sizes are going to be labeled by pi. So block sizes for this parabolic are pi 1 up to pi n, pi L, let's say. And inside of here is my Weyl subgroup, which consists of upper triangular matrices. And so these are two subgroups of the finite group of Lie type. And the preimage of these are the groups that I really need to make contact with. So this is so I is the Iwahori subgroup, and I pi is a parahoric subgroup. And those are the things. So the things on the left side are what I will call affine, and the things on the right side are what I'll call finite. And somehow the whole picture that I want to, the whole game that I want to play is how do we go to affine? We're going to pretend we sort of know about finite, and that will. So the most important thing here is that G is a disjoint union, so I'll need this notation. Too many W's in my, because it's the iPad, it's going to be hard to read, but these G decomposes into Brouillard cells indexed by the Weyl group. So W is going to be everywhere, and W is the Weyl group. And of course, this P pi creates its own, if you look at just the cells that are inside of P pi, that will be the subgroup W pi. So a Young subgroup or whatever you call it. So W and W pi are going to be two crucial pieces of combinatorial data that I'll need everything. All right, so this is the loop group setup. And actually, already, if we can sort of go back here, you'll see that here we had an I pi, and here we had an I. And those are really the I pi and the I that I'm dealing with here. So I'm going to very slowly put together what these formulas mean. Okay, so that brings me to loop groups. What do I want to define next? So I think I can just go ahead, and introduce these affine Lusztig variety. Oh no, I need notation. Of course, I need some notation. So notations. So the first notation is going to be curly W, and that's going to be an index set for this first sum. So this is over curly W, and curly W is an index set for the conjugacy classes of the Weyl group. All right, so this W that's over here, that's the Weyl group, and I'm going to index conjugacy classes. So Adriano Garcia and Heyman's life is all in type GLM. And I'm going to have many different sets that are all partitions of N. And one of them is this conjugacy classes of the Weyl group. For type GLM, the Weyl group is the symmetric group, and the conjugacy classes of the Weyl group are indexed by partitions of N. All right, so inside of the partitions of N, so gamma nu here is a minimal length element in the conjugacy class W nu. So when I put a nu on the curly W, that indicates the conjugacy class labeled by the element of curly W. And gamma nu is a minimal element. So if you think about just in the symmetric group, what's your favorite representative of a conjugacy class? Well, it's a cycle which has as few crossings as possible. It's as nice as possible. So that's what gamma nu is. And so that's already getting us some parts of this formula here. This gamma nu and this nu, these are labeling conjugacy classes in the Weyl. So that's the first piece of notation. The second piece of notation that I need is C, and I like to put a unipotent on here. So this is an index set for unipotent conjugacy classes in G. So G is this group on the right here, and I'm going to look at unipotent classes in there, and then U mu is going to be a representative of the corresponding conjugacy class labeled by mu. So that's a unipotent class. So of course I only know one group related, so this looks like unipotent means it's got ones on the diagonal and it's got blocks. So it looks like this. And it's in Jordan form. And of course, if you're really going to do combinatorics, you need to choose, make these choices of Jordan form with block sizes. Some mu1 to mu1. And so when I'm trying to make contact with Garcia and Heyman, I really do need to make all these choices to get their formulas. But for now, we can just choose any representative of that class. So now you can see here that if I keep going back, I know that's frustrating, but this U mu, what is it in my head? It's a unipotent element of Jordan form mu. So whatever this object is, it depends on this unipotent element, and it depends on a conjugacy class in the Weyl. So that's almost the notation I need. I need one more piece of notation, which again is partitions of N. So curly P is conjugacy classes of standard parabolics. So standard parabolic means a parabolic subgroup that contains B for me. But that just means that when I'm looking at this parabolic here, I am choosing the block sizes, but I might as well choose those block sizes in increasing order or something so that I can make contact with partitions again. So again, curly P is the index set for this sum in the modified element. So the modified elements are actually having to do with parabolic subgroups. And again, in type GLN, that's indexed by partitions. I can choose the block sizes according to the partitions. All right. Good. So now the only thing that we have remaining to tell you is these things and the kappa and the 1. But let me start with these varieties. So the first one is the affine Lusztig varieties. So affine Lusztig varieties, and this is what's going to correspond to the integral form Macdonald elements. So I denote it by a y inverse because in my head, the reason I call it y inverse is because in my head it's an analog of a Springer fiber, and a fiber should be a y inverse. So I don't know what you guys like to label your Springer fibers by, but that's why I put a y inverse. And then I've got down here a Schubert cell with respect to this Iwahori subgroup, and I've got u mu, which was my unipotent element. And this consists of all flags. So for me, a flag is a coset of G tilde mod I. So the affine refers to the G tilde, the left-hand side of my loop group picture. And G tilde mod I is the affine flag variety. And yi is just an element. It's a flag in that affine flag variety. So that's what I think about it. And then I take y inverse u mu y. So this is the adjoint action on the group form. And I check whether that's in the Schubert cell corresponding to gamma nu. So gamma nu was a very special element of the Weyl group. And if you already know some of these games and you're being very careful, it's very strange that I'm looking only at the finite Weyl group, but I am only looking at the finite Weyl group, even though this is an affine Lusztig variety. All right. So the ordinary the ordinary Springer fiber would be the case when gamma nu corresponds to the identity class. If we just took the identity out. So far, so good. So that's now we've done a lot of notation, but I claimed at the very beginning, I'm just a combinatorialist. I just want to count the number of points. This is the object I want to count the number of points for the integral form. Okay. For the modified form, I want to count a different guy, which are the pi parabolic affine Springer fibers. Okay, so that is the other one, which is yi pi inverse of u mu. And it's got almost the same definition, except that I'm going to take partial flags. So I'm working in G tilde mod I pi. So those are partial flags for that parabolic. And then I take y inverse u mu y, and this should be in I pi. So that's an ordinary parabolic Springer fiber, except that I've done it now. Maybe I don't know if the spacing will work, but let's try. Let me copy these two things. And put them also down here. Yeah, mostly fits, right? So hopefully now you've got them all on one slide. We've got the Lusztig varieties, which I'm going to count the number of points in Lusztig variety and put them in a generating function. And I'm going to count the number of points in the Springer fiber and put them in a generating function according to the different parallels. And my claim is that these objects are somehow the Macdonald polynomials that we've been studying with Garcia and Heyman. So I haven't been working with them, but the combinatorial community has been studying. All right, so ask me questions if you feel like interrupting. Please do. I feel better. Okay. Okay, so the next step I want to do is tell you what this kappa and this 1 are, because I haven't yet told you that. And of course, anybody who knows me knows that pretty much I can't do anything without coming to a Hecke algebra. Okay? So I'm going to think about a Hecke algebra. And my Hecke algebra, so remember that G is GLN of Q, the finite field of Q elements. And 1b to the G in my notation is going to be the induced representation from B to G of the trivial. B is just upper triangular matrix, ordinary Weyl. So this is a coset space, just like we saw in John's talk, in its representation corresponding to the flags. And the Hecke algebra is the endomorphism ring. Think of it as a complex representation. So for me, all representations will be complex. And I take the G endomorphisms of this. So that's an endomorphism ring. That's a small finite dimensional algebra. And that's the object that I know that I want to study. So H has a basis, a very convenient basis, and very convenient multiplication rules. So the basis is called TW. That's the standard basis coming from the Schubert cells for me. And maybe the point of how I think about it is that when you write down the multiplication rules in terms of this basis, it's always polynomials in Q. It just works out that way. It's very easy to compute it. And if you set Q to be 1 in those polynomials, then this Hecke algebra becomes the group algebra of the Weyl group. So this Hecke algebra is just a deformed, I think of it as the group algebra of the Weyl group, but with a Q floating around all over the place. And the same thing with these, and I want you to think about it as a deformed version of the Weyl group. So the TWs are just the W's in the Weyl group, except that I'm looking at this version. Okay, so I want to make a note over it. I'm going to abuse my setting a little bit and use some notation that I haven't yet defined, but I still want to make the note here. And that is that, suppose I was looking at a Lusztig variety, but for the finite case. So this is the same kind of thing, except that I'm not working with I, I'm working with B. So just go to the right-hand side. And I want to count the number of points. Then there's a very nice way to say it in terms of Hecke algebras, and that is you take the trace of U mu. Remember, U mu is my unipotent element, and gamma nu is a minimal length element in the conjugacy class of the Weyl group. And I act by those two things on this flag representation and take the trace. So I can really view it as just the trace of two elements acting on this representation. And that counts the number of points in the Lusztig variety. So actually, Tom Halverson and I, many, many years ago, studied these bitraces. We called these bitraces, and we studied them to determine some of the combinatorics of traces on the Hecke algebras. And we were pretty on that. We knew that we were counting points of variety. But at that time, the focus was in terms of Hecke algebras, and that's really helped me a lot. So I can write a similar formula if I take the trace of U mu on 1. So I'm going to use a notation in a bit. But this is just this representation here on the right is just partial flags instead of full flags. And if I just take the trace of U mu on that, that is exactly the cardinality of an ordinary finite parabolic Springer. So whether you can compute it or not, I'm just saying that I have another part of the reason I want to think about Hecke algebras is because it gives me a nice way to say how you might count. Okay, so now let me introduce the elements of the Hecke algebra that I need. Kappa. Okay, so the first element I need is this 1 pi. So I call that a pi parabolic projector. The pi parabolic projector is 1 pi. And it's an element of the Hecke algebra, which means that it's a linear combination of the basis elements. And this algebra is like the group algebra of the Weyl group, so the basis elements are indexed by the permutations, the elements of the Weyl group. And there are some coefficients here, which I'm going to call W pi. And these are very simple. W pi is equal to 0 or 1. CW pi is equal to 0 or 1. It's equal to 0 if W is not in that parabolic subgroup of the Weyl group. And it's equal to 1 if W is in the parabolic subgroup of the Weyl group. So it's just a characteristic function, except that now I'm viewing it inside the Hecke. All right. So if I can go back just a little bit, I know. But when I look at this modified Macdonald element, I said it's a generating function, but I have placed this generating function inside the Hecke by putting this, keeping things together with this 1 pi. And I'm going to do a similar thing with the kappas. So the Geck, this is called the Geck-Polynomial basis. Now, this is the basis of the center of the Hecke algebra. So the center of the Hecke algebra looks like the center of the group algebra of the Weyl group. And the center of the group algebra of the Weyl group, we know some favorite bases of that. One of the favorite bases is the minimal idempotence, minimal central idempotence. Another favorite basis is the conjugacy class sums. So this conjugacy class sums is the basis that I'm trying to get here. So this basis is called kappa nu. And so there's one conjugacy class sum for each conjugacy class. And this kappa nu is, again, it's a linear combination over the elements of the Weyl group of the basis elements. And then there will be some entries here, some coefficients, which will be polynomials in Q. All right. But the function of these things, so first of all, if you take kappa nu gamma mu, so let me write the formula and now explain. So gamma nu is minimal length. See, the Hecke algebra is very finicky about lengths. So that's why I have to put minimal length everywhere. If I were just working in the Weyl group, then central elements are invariant under the whole conjugacy class. But when I'm working in the Hecke algebra, central elements are not exactly invariant under the whole conjugacy class. So I have to be a little careful. So if gamma nu is minimal length in the conjugacy class, W mu, then this coefficient is 0 or 1. All right? But when I'm not minimal length, then I have some other garbage that's necessary just to make it central. So I'm that's the first condition is already the most important one, but the second condition really is that it's central. But I will also write this this kappa. When I evaluate these coefficients at 1, then it's very simple. Then it's a conjugacy class. So if W is in the conjugacy class nu, or W is not in the conjugacy class nu. So this says that the Geck-Polynomial basis element, when you specialize Q equal to 1, it becomes the conjugacy class. So I just produced a special element inside the Hecke algebra that is an analog of conjugacy class. Maybe we'll copy the, oh, I can just copy them again. Yeah. So here's my same two formulas again. So I'm just generating functions for Lusztig varieties and Springer fibers, but I'm putting them inside the Hecke algebra with special elements. That's the moral of the story. Okay, so I do want to give an example of these kappa. So this matrix C, let me look first at this CW pi. So CW pi was 1 if it's in the parabolic subgroup of the Weyl group, and 0 if it's not in the parabolic subgroup. I call this, so it has rows indexed by the Weyl group, and it has columns indexed by standard parabolics. So it's not a square matrix at all. For GLN, the Weyl group is n factorial rows, and the number of partitions is much less than n factorial. So this is what I call the contraction matrix, and because it somehow takes a lot of rows and has very few columns. So I call that the contraction matrix. And the matrix of these kappas, so maybe I should call it kappa Q, because it's got polynomial entries. So this has rows indexed by the conjugacy classes in the Weyl group, which again in type A is partitions of n, and columns indexed by all the permutations, the whole Weyl group, and this is the expansion. Let's see how let's see the clocks. So, and I end at 11:20. But we're going. All right, so this contraction matrix and expansion matrix, let me just give an example. So if G is GL3, FQ, then the expansion matrix, it has rows indexed by partitions of n, which I was influenced by Macdonald, so I use this notation for partitions of n, but however you index the conjugacy classes of the symmetric group S3, 3 of them. And then it has columns indexed by permutations, which are in the symmetric group S3, which for me look like these funny pictures. And for you, I don't know how you write functions from 3 elements to 3 elements, but that's how I write them. And this matrix has 1, 0, 0, 0, 0, and then 0, 1, 1, because those two permutations are minimal length in their class. And then it's got a Q here, where it's not minimal length in the class. And then it's got a Q minus 1 and a Q minus 1. And you notice that when you specialize Q to 1, Q minus 1 becomes 0, so that this is actually a conjugacy class. It's messy, but and this one is really just the conjugacy class. So we can build these matrices corresponding to this Hecke basis. And the contraction matrix has rows indexed by the permutations and columns indexed by the partitions in this case. And the partitions are now, they are really indexing parabolic subgroups. Whereas in the expansion matrix, they're indexing conjugacy classes. So outside of type GLN, these are not necessarily the same size exactly. And this matrix is much simpler. It just tells you, is your permutation an element of that parabolic subgroup of the Weyl group or not? We have just two matrices, which now we're starting to get to the combinatorics. So we really got physical matrices we're looking at. All right. So that's the game. And I think now these formulas, integral form and modified form, at least they make sense. I hope I haven't left out any. All right. Great. Maybe we'll copy and paste that one more time, just so we have it. So I think now I can go to symmetric functions, which is the last section I'm going to do, which is the classical case. So this, of course, is type this is part of what I want to claim. It took me, so part of the reason I couldn't figure out what to do or what these meant was that the symmetric functions really are the part that's just type GLN in my head. So this is actually a very important question, which I'm totally avoiding. Because, these, I'm writing cardinality. I'm telling you I'm counting points. But of course, these are affine Springer fibers and affine Lusztig varieties. And they are not over the very special cases when those happen to be finite. So these are really infinite. The answer is infinity. Okay, so for these cardinalities. So of course you have to do it more intelligently when you count the number of points, is you have to take your affine flag variety and divide it into small finite pieces. And I'm just going to use the cell decomposition from the Schubert cells. And then I need a statistic on the Bruja cells, on the Schubert cells. And I like to use t to the length of w. So the t is keeping track of the length of the corresponding permutation of the affine Weyl group. And then the intersection of the Lusztig variety with the Bruja cell keeps track of the q. Thank you. All right, so we totally avoided that. But it's a very important point, and you can't do these counts exactly unless you have some exact statistic for that t. All right, so now let me go to the symmetric functions. So the classical integral form, Macdonald polynomial. So I'm going to definitely say it not in the way that Macdonald said it. So he did call it J mu of x qt. And it is the sum over partitions. And so this is what I'm claiming, is that what Macdonald wrote secretly was the cardinality of an affine Lusztig variety times m nu, where m nu is the monomial symmetric function. Symmetric. Okay, so how did I come to why this could be? So I should put, this is of course Macdonald polynomial in the integral form. And why did I come to trying to do something of this nature? And that is because for the modified Macdonald polynomial, you can write it, so it's h mu, now it's got variables x, q, and t, and you can write it as a sum over pi of the cardinality of the affine Springer, parabolic affine Springer fiber over u mu of m pi. And this is the theorem of Mellit. So Mellit said that the modified Macdonald polynomial defined by Garcia and Heyman could be interpreted this way, as the cardinality of an affine Springer. And what I'm saying is that the original integral form of Macdonald polynomial that Macdonald wrote down can be interpreted this other way as Lusztig variety in terms of Lusztig. So that's my point. Now, so let me go back a little bit, because I've chosen here to put this integral form not in symmetric functions, but inside the Hecke algebra. And I needed to move to the Hecke algebra to go to other types, because in other types, the symmetric functions don't model the center of the Hecke algebra anymore. But in type A, this map is the same as the map of 1 and 1. So they have a very nice paper, which is about the Frobenius characteristic map for Hecke algebras. So of course, the Frobenius characteristic map for the group algebra, the symmetric group, is classical. And it's an important step that you know exactly how to make this Frobenius map from the center of the Hecke algebra to symmetric functions in the type GLN case. And that's exactly the one that I want to use to do this conversion. All right. Good. So I think we've got all these parts. So there's only one thing left to say, and that is, what was the original definition of the modified Macdonald polynomials? So the original definition of the modified Macdonald polynomials was through what's called the plethystic transformation. And that was, for me, something I never could figure out. What is this crazy plethystic transformation? So if you talk to Garcia, he will tell you that the modified Macdonald polynomial is related to the non-modified, the interval form Macdonald polynomial, by a formula where, so there's a constant t to the n of mu, which is, that constant is not a problem. But then he has this crazy plethystic transformation, and I won't even try to describe in this talk what this plethystic transformation actually means. It's not really difficult, but it takes a little bit of fiddling, which I don't want to do. But just that the original definition was this one. You take J mu, you plethystically transform it, and you get this modified Macdonald polynomial. And so I needed this plethystic transformation to be into my picture as well. So the way that I think about it then, now this, how do I get an extra page when the little thing is in the way? Okay. Oh, yes, thank you. Oh, no one wants to go back.
Yes.
Great. So let's let our new pi of q. So these will be some functions of q. These will be given by. You take the monomial symmetric function m nu, and you do this crazy plethystic transformation that Garcia tells you should do, and then you just re-expand it back in terms of the monomial symmetric. So this is our new pi of q. Now, if you were thinking general type, at this point, something very weird is happening, because you might remember that the nus were labeling conjugacy classes of the Weyl group, and the pi's were labeling standard parabolic. So there's something funny that's happening, but this is the right thing. And so this is the theorem from a combinatorial perspective that I came across, and that is that these R's, this plethystic transformation, so that just the combinatorics of the plethystic transformation is this matrix of R's. And the R's are the sum over the symmetric group, which is the Weyl group in this GLN case. And then there's a factor, q to the n minus the length of nu, which is a normalization. And then there's kappa, and then there's c. You might remember that I called kappa the expansion matrix, and it was not square. It was a big rectangular. And C was a contraction matrix, which was also not square. So the point is that you take, so up to some normalization, so the cardinality here of p pi mod b, this relationship between the 1 pi's, which are the parabolic projectors in the Hecke algebra, and the kappas, which are the get-Fouquier basis in the Hecke algebra. So that relationship is captured by these expansion and contraction matrices. And if you do expansion and then contraction, it converts you from the get-Fouquier basis to the parabolic projector. So it really is something that moves across it. And that conversion is exactly the plethystic transformation. I mean, but once you get the normalizations, right? So it explains, at least for me, this last formula explains why. Oh, I should add one thing here, and that is that this is a shadow of everything that's happening. So Lusztig varieties. So there's really a geometric picture between Lusztig varieties and parabolic Springer fibres, parabolic. And that's happening on the geometric level. And I learned this conversion, what is essentially in the works of Iwahori, who taught me how to play with these things. And this formula for R is a combinatorial shadow of the actual relationship between the Lusztig varieties and the parabolic Springer. All right, I think I'll stop there.
So I want to ask about, so the center of the Hecke algebra, and sometimes the interpret as the symmetrical hammer uses repeat elements. Is this relevant to your picture?
I don't know. It's a good question. I don't know. So there are many questions about the structure. So how do I say this? There are many things that I know about the Hecke algebra, and now there's some relationship to Lusztig varieties, and I'm trying to transfer that information across. But I'm at the very beginning of that. I really don't know. There are many things, in particular Murphy elements in Hecke. I don't know what they mean in terms of the structure of the Lusztig varieties.
Other questions?
And you formulated them for the theorem that's at 8 case. So in cases of symmetric
So
this time, some of the polynomials may not be just simply symmetric polynomials.
So I don't. So these integral form and modified elements in the Hecke algebra, they will exist in all types.
That's what.
So the only question is, what would a Frobenius characteristic map be in other types? And in other types, I don't have a good answer for that.
And one more question. So always there should be some homological and includes the first shift.
Oh yes, of course. I'm just doing ordinary point counting. So growth and Lefschetz takes care of everything for what I'm doing. Yeah, you can easily set up growth and Lefschetz to produce the Frobenius fixed points and count the number of points over FQ as I'm doing.
Thank you.
Do you have a sense of why Garcia thought this plethysism was the thing to be looking at?
Well, fortunately, I was there and saw it all happening at the time. And so certainly they were working in the case when t is 0, which is the Hall-Littlewood case. And those are the finite Lusztig varieties. And so there, of course, we had already Macdonald's book, and we had a lot of stuff. And you could really see that the plethystic transformation captured the conversion to the geometry in chapter 4 of Macdonald's book. So that was how they came up with that transformation. The thing that was striking at the time was that the same transformation would work for Macdonald. And we didn't know at that time, but I think this explains these things.
Okay, so I'm trying to ask, like, for this kind of, like, I'm not sure about this kind of polynomials, but for this kind of polynomials where there are common points, let's say we replace that minimum as elements, it's like for some kind of geometric study of all these kind of related varieties, it's reasonable sometimes to replace this kind of minimum as element with other, also sometimes substitutes for that, like.
Yeah, so I mean the structure of the so what the question, the way that I would like to say it is that if I changed this gamma nu to a different W, then what would be the structure of that Lusztig variety? And there is a relationship that the structure of the IWI is related to the one for I gamma nu I by a sequence of like kind of like blowups or vibrations.
So for those kind of one time, so we could go back to the same.
So how to package all that information into generating functions, I don't know. I know that physically you can take the Lusztig variety and derive the other one, but I don't know how to package it in general.
None of us maybe have any other questions for offline, so to speak, and thank you again.